All right, back from break. So we had started talking about different stages in a star's development, and that for stars with enough mass, the core temperatures can just, over the lifetime of a star, the core temperatures can actually become higher and higher. The hydrogen fuel runs out in the core. Gravitation begins to collapse the core even more, but that gravitational collapse raises the temperature, and then additional fusion reactions can begin. So this is showing a star where helium is now fusing. This is a medium to high mass star because helium reactions are taking place. We do expect the sun, maybe in another 4 or 5 billion years, the hydrogen will become depleted in the core, and that additional collapse of the core will raise the temperature enough that the sun will undergo helium fusion into elements like carbon or oxygen. Part of that process is the outer layers of the star then get pushed outwards. Once we get the shell fusion taking place, like we're seeing here with the hydrogen fusion, that leads to expansion of the outer layers of the star. So we're expecting the sun's going to get bigger and bigger in the sky. The surface is going to become more and more red as the layers spread out. We've seen this. As the layers spread out, even though the luminosity has not been reduced, the luminosity in these stages actually goes up. The outer layers spread out, and that means that the surface temperature lowers even as the luminosity is increasing. So again, we do expect that the sun will go through this stage, and that would mean the sun would get bigger and bigger in the sky. Now this is a process that's going to go on through tens or hundreds of millions of years, but the sun gets bigger in the sky, gets more and more red. It's going to get so big in the sky that the outer layers of the sun would actually likely reach the orbit of Earth. And so you could have the entire sky fill up with the sun, while the whole sky becomes red from the material of the sun. Though the fusion is still occurring just in the core, not in these outer layers, but the outer layers of the star, of the sun, would be at several thousand Kelvin. So that's going to impact planet Earth. So we've got to make some long-term plans for that. So anyway, it's saying that the classification of the star is going to change. You know, here is a star, maybe kind of like the sun, with a certain surface temperature and a certain overall luminosity. But as the carbon fusion kicks in, the luminosity goes up, but the outer layers spread out, and that means that the surface temperature actually lowers. And then eventually, once those outer layers spread out, that reveals the core, and now the temperature becomes much higher. Once the outer layers have spread out, they are no longer part of the star. That opens up direct exposure to those inner layers of the star, and those are still at really high temperatures. So quick outline here. Let's see, low mass, medium mass, high mass stars. On the main sequence, so here are the low mass, medium mass, high mass. Now it's a continuum here of the different mass stars. How long do these things survive? The low mass stars are going to live hundreds of, that's gigayears. Those are billions of years. Low mass stars could survive hundreds of billions of years. Medium mass stars like the sun, maybe 10 billion years. A high mass star, maybe only a billion years or so, or less. And that's because if you've got 10 times as much fuel, let's say you are a star and you've got 10 times as much fuel, well, you burn the fuel 10,000 times faster. So stars, as they go up in mass, you would think, well, they've got more fuel to work with, and they do, but they burn it so much faster. So think of it as, you know, an SUV versus a, you know, a compact car. Anyway, let's see. Yeah, here we go. So everybody goes through a hydrogen to helium phase in terms of fusion. And those stars, because of their surface temperatures and their luminosities, are classified on the main sequence. The stars that we see, that when we plot their luminosities and their surface temperatures are on that pattern of the main sequence, those are stars that are still undergoing hydrogen to helium fusion. Now, the red giant part of the HR diagram consists of stars that are fusing, say, carbon into oxygen or into silicon and iron. Now, the low mass stars, they're never going to have temperatures high enough in the core to fuse helium. So all they have is the hydrogen to helium stage, and then the fusion shuts down. But remember, that could go on for hundreds of billions of years. That's longer than how long the current universe has been in existence. So all of the low mass stars that have formed, they're still out there, and they're going to be shining for a long, long time. These medium mass stars, like the Sun, these shut down and become what we call white dwarfs. The highest mass stars are able to fuse elements all the way up through iron, and then they undergo a core collapse supernova. The gravitation is so large in the highest mass stars that we can actually have reactions where protons turn into neutrons and the electrons turn into neutrinos. Now, have you ever seen a reaction like that? And you go, yeah, that's kind of like beta decay. So what's happening in a star, the gravitation becomes very, very intense. And if you remember, it's the electrons that are big and bulky. So gravity is squeezing on those electrons. Now, is there a way that the star could continue to undergo collapse? Well, if the electrons turn into neutrinos, those neutrinos are just going to fly off, and they're not going to contribute to the bulk of the star. And so that enables the star to eliminate, gets rid of its electrons, those become neutrinos, they fly off. The protons at the same time, in that coupled reaction, turn into neutrons, and we have what's called a neutron star. So these were first predicted to exist. Theorists took a look at gravitational forces in these really high mass stars and said there would be enough to set off these kind of particle reactions. And so, and now we have observations, we've had this for a number of years, of neutron stars, or an even further collapse. If a neutron star's gravity continues to collapse the star, then it becomes what we call a black hole. And we'll talk about black holes a bit. But so you can see these high mass stars have some extreme kind of final states that they can become. All right, here is the timeline of the universe. So there was this high temperature, high pressure plasma state that existed everywhere in the universe. The Big Bang was not an explosion that took place at one location. Let's see, the whole universe was in a hot, dense state. That's like the theme song to the Big Bang Theory TV show. And that's what it was. So the whole universe was in a hot, dense state, consisting of neutrinos, electrons, protons, neutrons, photons of really high energy, just zipping all over the place. And this is referred to, this plasma stage, referred to as the Big Bang. If we label that as t equals 0 and say, we're not sure what's going on in earlier stages, but something led to this. Then what happens is we can run forward in time since that, and what we've seen are formations of stars and galaxies. So due to gravitational forces, we see the formation of stars, formations of galaxies. The high mass stars have gone through these rapid processes of fusion. They have gone through what we call nucleosynthesis, the formation of heavier and heavier elements. Now, high mass stars then have these high fusion rates. They have generated the early parts of the periodic table. They have a very short lifetime, and then they blow themselves up. During these supernova explosions, more of the periodic table can be generated. So these high mass stars have rapid fusion, short lifetimes. They generate all the elements of the periodic table, and then they blow themselves up and scatter this. This is where we're getting that dust from. Little specks of all of this, this nucleosynthesis that the star has undergone. They have made planets like Earth a possibility. If we look out into the universe, what's the universe made out of? If we look at the atoms that we see out in space, you know, somewhere between 95 to the high 90% of the atoms are either hydrogen or helium. So where have all the heavier elements come from? And they've come from these supernova explosions. So the categories we have in astrophysics, there are three categories of elements. Category 1 is hydrogen, category 2 is helium, category 3 is everything else. Those are the heavy elements. Those are the ones that have been formed from nuclear fusion inside stars. And what has happened over the lifetime of the universe, if you look at the oldest regions of galaxies where star formation has been shut down now for billions of years, you'll see a slight enrichment in heavy elements. But if you look at regions where star formation has continued for billions and billions of years, in our region of our galaxy, at the time the solar system formed. So our best estimates are that the solar system formed maybe 4.5 billion years ago. That would place it about 9.3 billion years into the formation of the galaxy. Currently, we're going to say we're at about 13.8 billion years from the Big Bang. At the time this solar system formed, the concentration of heavy elements was, 2 or 3%. Well, that's the stuff planet Earth is made out of, and that's the stuff that we're made out of. So all the stuff around us is made out of these heavy elements for the most part. And that process has continued. So if you look at stars, systems that are currently forming in the Milky Way, we've now reached concentrations of maybe 4% heavy elements. So anyway, these heavy elements make the universe a lot more interesting, right? Having these heavy elements means planets like Earth with solid surfaces can form. And that's kind of the story of nucleosynthesis within the universe. So I always feel like we should have, there should be an international holiday, right? Celebrating, well, Thanksgiving is kind of like that, right? So at Thanksgiving, I'm always, people are going around the table saying what they're thankful for. And when it comes my turn, I always say, well, I'm thankful for high mass stars. Look at what high mass stars have done for us. They have run through their fuel very rapidly. They've generated all the elements, and then they have very selflessly blown themselves up, provided all of these elements for us, for the planet that we live on, for everything around us that's familiar is made out of these heavy elements. High mass stars, I am thankful for high mass stars. I'm sure, try that out at the, next Thanksgiving, at the Thanksgiving table. Remember to let people know how thankful we should be for high mass stars. All right, let's see what other kind of interesting things are going on here that we might want to talk about. We had talked about supernovas. We had said that supernovas can occur if a star has just too much mass. So for the stars that have the most mass of all, gravitation eventually collapses the star, and we have what's called a core collapse supernova. But that's not the only way a supernova can happen. What if we have a star? Now here's a double star system. So here's a star and there's another star, and they're both part of the same star system. One of the stars has already gone through a red giant stage. It is now in a white dwarf stage. It did not undergo a supernova. It did not have enough mass on its own. But what happens if its neighbor now goes through a red giant stage where the outer layers spread out? Some of that, it's possible, can be acquired by a companion star. And that can push that star over the limit. This star by itself did not have enough mass to undergo a core collapse supernova, but now it's being donated additional material from a companion star, and that can set off a supernova. Now what's interesting about these supernovas is that these supernovas occur when we cross a threshold. So when this star, the companion star here, when it gets just to enough material that it collapses, the core collapses, and it blows up, every one of those stars occurs at about the same amount of material. And so those are really useful. We can actually use these to measure the distance to very, very distant galaxies. If we see a distant galaxy where one of these supernovas is taking place, these are referred to as type 1a supernovas, and they all have the same luminosity, and that allows us to determine distance out to those galaxies. It turns out that that's a good way to measure distances. All right, I think we're going to finish up the chapter with, finally, talking about a little bit about general relativity. Now, we already had a chapter on special relativity, but it turns out that we need to go back and take, once again, we need to take a closer look at space and time, and figure out how the properties of space and time are important in understanding how the universe will be developing. Now, general relativity is an extension of special relativity that Einstein came up with. And general relativity includes gravitational effects. Special relativity didn't do that. It didn't really talk about gravity or what gravity is. But within general relativity, Einstein makes a couple of dramatic kind of explanations as to how space and time are put together. Within general relativity, Einstein points out that space itself is not fixed. And it's not Euclidean. So the geometry that we're familiar with, the geometry that we learn in our geometry classes, doesn't necessarily apply to the universe as a whole, not the university, the universe. So one of the predictions that Einstein made was this. Einstein said that gravitational effects can be replicated with acceleration and vice versa. Now we saw this way back in Physics 3A, that gravitational fields, for example, have units, the very same units as an acceleration. Now, Einstein promoted this idea to kind of a principle and predicted that in a gravitational field, a beam of light would be observed to bend, because if accelerations create the effect, then so should a gravitational field. And observations were made that show that Einstein's prediction was correct, that light does bend in a gravitational field. And this is kind of a description as to how some of these experiments were done. Here are observers on Earth looking at light coming from stars 1, 2, and 3. During a solar eclipse, the sun's light is largely blocked out by the moon, and so during a solar eclipse, light from a star just outside, looking into the sky, just away from the sun's location, light from stars are actually going to be bent a little bit, and observers were able to see this effect. So that was an important observational confirmation of predictions from general relativity. Another prediction from general relativity is, again, because light is going to follow a curved path in a gravitational field, you could have the very same object. So here is a very distant, high luminosity galaxy. Now, there's these are called quasars. So quasars are these very luminous, very distant galaxies. But light from this galaxy, so there's an actual image of this, traveling through a region around something else with a lot of mass, can actually bend the light to where we get multiple images. So there's an example of where we're actually getting 4 or 5 images of the very same quasar, the very same distant galaxy. So with general relativity, we've got the possibility that space itself is curved. And by curved, we mean that it doesn't have familiar Euclidean geometry, that there could be a curvature that goes along with it. So the most familiar example we have with this is kind of the surface of the Earth. So the surface of the Earth, when we follow paths, if we pick a couple of parallel lines on the surface of the Earth and we follow them, we find that these parallel lines begin to converge. So if we went to the tile store and we found out that there was a nice square set of tiles, and we thought, oh, it would be nice to cover the whole planet with those square tiles, we find out we can't do that, because when we start laying the tile down, we find out that those what look like parallel lines are beginning to converge. And that's due to the curvature of the surface. Now that's called positive curvature. There's also what's called negative curvature. And that would be if we took those two tiles and as we began laying them down, we found out that what looked like parallel directions were actually diverging. They were spreading away from each other. We were starting to see gaps in the tiles. So general relativity says that we can have either positive or negative curvature, and that curvature is not just two-dimensional, but three-dimensional. So if we think of space this way, let's say we get a bunch of cubes, and we decide that we want to fill all of space with a bunch of cubic boxes. If space is Euclidean, then as we start stacking all the boxes in space, it works. No matter what direction we go in, we can keep adding more of these cubic boxes, and they will fit, together as a bunch of cubes, as you would expect for Euclidean geometry. But if space is curved, then that would say that when we start stacking boxes along some direction, that they start to converge into each other. They can't fit. There's not enough space to make everything fit. Or if it was negatively curved, then what we would find is that we're stacking the boxes, but there are gaps. The boxes aren't filling the space. There are these other sections of space showing up. Now, an analogous example of that would be to draw a point on the surface of a spherical surface and then draw circles around that point. Now, if the surface were Euclidean, if it were a flat surface, then every one of those circles would have a circumference given by 2 pi r. That's the formula we learn in our geometry classes. If it's positively curved like this, then it turns out that the circumferences we end up with are going to be less. They're not going to be equal to 2 pi r. They're going to be something less. So curvature is a funny thing, especially when you say all of three-dimensional space, and general relativity says it's not just the 3 dimensions of space, but that time is also affected by this. And so very generally, if we think of this 3-dimensional positive curvature of space, or this 3-dimensional negative curvature of space, then as we move away from it, any circumferences we measure would be less than 2 pi. Now, if we're thinking 3-dimensionally, then we would have to think of spherical surface areas. If it's positively curved, the spherical surfaces would be less than 4 pi r squared. And that would indicate that the overall density of the universe is higher than what general relativity tells us is kind of a critical density. So there is a critical value to the density, and if we go higher in density from that, we end up with positive curvature. If we go lower in density compared with this critical amount, then we end up with negative curvature, where the circumferences get bigger than we would have expected and the surface areas are bigger. So it's kind of interesting that we've got these possibilities. Now, the familiar geometry that we've learned is Euclidean geometry, and it's referred to as flat. Euclidean is probably a better word for it. Euclidean geometry means that Pythagorean's theorem works in all 3 dimensions. And so if we take x squared and y squared and z squared and add those together, that will give us a distance squared. Now, I've written this in calculus terms because there's a branch of mathematics called differential calculus. We're not going to do any of it, but it says that we can explain all of geometry of any surface, of any volume, by showing step by step how each piece is connected to all of the others. And so with this definition throughout, then we have our old familiar Euclidean geometry where surface areas of spheres are 4 pi r squared and circumferences of circles are 2 pi r. Now, general relativity says that is a possibility, but it only occurs right at critical density. So it says there have to be just the right number of stars and galaxies and other materials within space in order to give a critical density if we're going to have Euclidean geometry. So the evidence right now suggests that we are very close to no curvature at all, and that's kind of interesting. We're thinking, astrophysicists are thinking that we know that this sort of stuff happens, the positive and negative curvatures, over certain scales within the distances within the universe, but kind of the largest scale of curvature show that on average we're very, very close to critical density. And we're thinking that there's some kind of a reason that has happened, because we do see the effects of general relativity locally around planets and stars and such. So let's talk a little bit about black holes too, I guess. In the extreme limit, we say that when a star collapses, if we get a significant amount of mass in a star, there's enough gravitation from that we don't know of anything that prevents the collapse. And that suggests that the star could collapse down to just a point. It could collapse down to just one point. And we call that formation a black hole. And a black hole is kind of interesting. I mean, one way to think of it is that the curvature itself is so strong that light doesn't... There are no paths along with objects can travel back outside of the region surrounding a black hole. Now, so the way a black hole would work is all of the trajectories of any object moving in the region around what's called the event horizon. There are trajectories that where you would cross the event horizon headed towards the black hole, but once you've crossed that event horizon, there are no paths going forward in time that would allow you to travel back out. There just literally are no paths that lead back out of that region. It's an effect due to the curvature of space-time. Now, for us, what we're interested in here, I guess, is taking a look at the expansion of space. This is one of the predictions from general relativity. So what we find is that if we go way back in time, what we have evidence for is that space itself has been expanding. So ever since that Big Bang phase, ever since the very early high temperature, high density period in the universe, space has been expanding. And you might ask, well, how do we do that? What is it we've observed that lets us know that space has been expanding? And what we see is that the light from distant galaxies is redshifted. So we would expect that if there's just random motion of galaxies, that when we look at light from distant galaxies, some of it would be redshifted, indicating motion away from us. Some of it would be blue shifted, indicating motion towards us, just by, statistical chances. But instead what we see is that all of the galaxies, pretty much, once you get past a certain distance, all the galaxies are moving away from each other, and that rate of separation is correlated with distance. So if I look at galaxies that are, 20 million light years away, there's a certain rate of separation with those galaxies, between us and those galaxies. If you look at something that's 40 million light years away, or 80 million, or 100 million, or 1 billion light years away, as you look deeper and deeper into space, this redshift becomes more and more pronounced. What that indicates is that during galactic time, that all of space has been undergoing an expansion. Now what we can do is we can do kind of an approximation. If we assume that there's kind of this uniform distribution of galaxies, galaxies are kind of distributed, scattered uniformly throughout space, and then that expansion is taking place uniform throughout the cosmos, then what we would say is that because of this separation effect, space is expanding, the galaxies are just being carried along for the ride. It's not that galaxies are racing through space, it's that galaxies have formed at certain locations within space, and as space itself expands, the galaxies are being carried farther away from each other. Now, light that travels, let's say, from galaxy A to galaxy B, when we have particles traveling through expanding space, this has an effect on those particles' wavelengths. So the wavelengths will get stretched out, and the amount of stretching that we see is going to be determined by how much of a redshift or how much of an expansion the light has experienced. So we can actually map this out. If light leaves galaxy A and arrives at galaxy B, during the time that it's traveling, its wavelength will be stretched out. Now, if the expansion has been very steady, and that's not such a bad approximation for us, so we can actually derive some formulas showing that the wavelength of the observed light when it arrives compared with the wavelength of the original light that left is given by lambda b over lambda a. I'm going to call that big R. I'm going to call that the redshift. And what we can show is that the redshift that occurs is given by the formula of E to the V over C, where V is the relative rate of separation. Now, they've given us a formula here. This is the formula for the redshift. This is the redshift from special relativity. So this is a formula we derived back in chapter 36, but that's not what's applying here. So this is not a special relativity effect due to velocity. It's actually a general relativity effect due to the expansion of space itself. So it's the fact that space is expanding that this redshift is occurring. So it's not a Doppler effect. We can't use the Doppler formula for this. Okay. Now this is a derivation. I'm not going to go through the details of this, but this is a derivation of the formulas that we had just written down. So what the graph shows is this. Let's say that we have galaxy A, and galaxy A is, we're going to use that as our reference. So the vertical axis is distances, and the horizontal axis is time. And galaxy A and galaxy B, way back when, were at the same location, but since that time they have separated. Now, it's not true that the galaxies ever were actually in the same space. It's saying that the two galaxies formed from a region of space where everything was collapsed into a much smaller, space itself was just much smaller at that time. So along these lines were the materials from which galaxy A formed, and along this region of space is the materials, and the galaxies formed pretty quickly. So if this is 13.8 billion years, the Hubble time, then the galaxies have formed within the first billion years or so. So within a few billion, within a billion years or so, galaxies have formed, stars have formed, and then they've continued to be carried away from each other due to the expansion of space. Now, the formulas we want to work from here, let's see what we've derived. There is a redshift formula that we wrote down on the page before. That's the wavelength of the observed light arriving compared with the wavelength of the light when it originated. And in the model that we have here, that we've developed, where the expansion has been steady, the ratio of the wavelengths will match the ratio of the distances. So x naught is how far the galaxies were separated at the time when the light left, and xh is the distance that the galaxies are separated now. T naught is the amount of time that had passed at the time the light left galaxy B, and time h, or the Hubble time is what it's called, is the current age of the universe. So going through all of this derivation, we've come up with these formulas. So here are the formulas that we're going to work in terms of. And I guess, yeah, we've got more that we can develop from this. That's what's going on. So let's just put some numbers down. The Hubble time, current numbers for that is like 13.8 billion years. Let's say that we have light with two different wavelengths. Now I'm trying to decide, I think this was an example they suggested. Oh, maybe not. Maybe it's our own numbers. Okay. So let's say that we have light that originated at 410 nanometers. That's a prominent line within hydrogen. And that it's observed, it's been redshifted to 740. Well, that ratio is 1.80. To find out when that light left galaxy B, we can take the Hubble time, divide through by that ratio, and it says that it left at the 7.65 billion year mark. How long has that light been traveling? Well, it's been traveling TH minus T naught, and that's 6.12 billion years. So this is a way to go in and at least get an estimate based on redshift as to how much time that light has been traveling. Now here's the other formula. So at what rate are the two galaxies separating from each other? And V is equal to C times the natural logarithm of R. So again, from these numbers, the R value is 1.8. The rate of separation of the galaxies is pretty high. It's 0.589 times C. About 60% of the speed of light is the rate of separation. Now, how far were the galaxies separated? At the time when the light left, we can take the T naught numbers and plug those in, and it says at the time the light left, there was a 4.5 billion light year separation between the galaxies, but now that more time has passed, the galaxies are separated by a greater distance. So we can keep track of the time the light left, the time is the light's arriving now, so that's typically at the Hubble time. And then we can keep track of the separation distances at the time the light left, and then at the time the light arrives, which is now. Okay, the book takes a little different approach. They use a Hubble law, and that's just showing the current rate of expansion. Let's see what else we have here. This is just giving us an estimate. Now we used a number 13.77 billion years. In this example, the textbook is using 14 billion years. Very similar numbers. I had looked up some values of currently what do we feel like is the best estimate for that amount of time. Now, the evidence that we have that this expansion has taken place is that at the time of the early universe, the early plasma state would have been filled with lots of photons. And we can look at those photons and see how much they have redshifted. So at the time when the universe was cooling down and the first atoms were beginning to form, the temperature at that time would have been about 3,000 Kelvin. Now what we can do is we can look at photons. The photons that we see that fill space now, they're not at a temperature of 3,000 Kelvin. They're at a temperature of 2.725 Kelvin. So if you think back to chapter 37, when we were looking at thermal radiation, those photons used to be at a thermal radiation temperature of 3,000 Kelvin, which means they had a peak wavelength that was in the red part of the spectrum or probably off into the infrared just a bit. But now they're 1,000 times cooler. And that has happened due to the expansion of space. So the expansion of space itself has led to a lowering of temperature, a lowering of energy of all of those photons left over from that very early phase in the universe. Okay, so here's another one of the timelines, and so the textbook presents this. Uh, they always have these birth of universe items here, and I always feel that's good to point out that we really don't know what occurred before the plasma state. So if we had a plasma state, we don't know what we don't know the reasons for why the universe was going through a plasma state at that time. It could be that the universe existed in some other form before that time and was going through a plasma phase. It could be the plasma phase repeats itself. In any case, what they're saying is, well, kind of the same stuff. They've got all these different eras labeled here. Notice the times on this: 10 to the minus 43 seconds, 10 to the minus 35 seconds. This is all happening within just a fraction, a tiny, tiny fraction of a second. It's really not till we get to this stage where we have, I feel like we have reliable evidence that the universe really did. Once you get up to this region here, a few seconds in, we certainly have evidence that the universe, the entire universe, went through a high temperature, high density plasma phase. That seems pretty reliable. That's based on the redshift measurements that we can see. It's also based on the abundance of different elements, or different isotopes of different elements. If we follow this from the first several seconds through the process, there would have been an early stage of nucleosynthesis that took place in the universe. So the nucleosynthesis would have been a period where about 25% of the protons were converted into helium. Helium fusion took place throughout the universe itself at that time because of the high temperatures. Since that time, we don't think nucleosynthesis has been taking place anywhere other than inside the cores of stars. But there was this very early period for just a few minutes. I know that sounds crazy to talk in those terms, but for a few minutes, the universe was at a high enough temperature that nucleosynthesis could have taken place, and we're able to calculate what isotopes would have been formed and their abundances. We do see that about 25% of the stuff in the universe, about 25% of the hydrogen of the protons, have been converted to helium-4, and then we have trace amounts of deuterium and trace amounts of different isotopes of lithium that match up with the predictions from this model, from an expanding space. So we do feel like we have pretty reliable evidence for that early universe properties. Okay, so what we can do is we can say this. We can say that, currently we are oh, I see. I was a little confused. They had this listed as 10 billion years. So if we say currently is right here is now, now would be, some number of years already occurring, but they're saying 10 billion or 20 billion or 30 billion years from now, what are the possible conditions that we would find the universe in? Well, right now, the best observation suggests that we could have an acceleration in the expansion. The expansion is actually speeding up. So the expansion of space is increasing, and if that's the case, most of the evidence suggests that, then we would expect that the universe continues to spread out. And it's not understood how the universe would ever collapse back on itself. Now, if it does, if we do have uh, for whatever reasons, a higher density, positive curvature, then the universe would collapse back on itself. If we have these lower densities, then the acceleration would be extreme. Right now we're probably, I'm guessing we're along the green line actually, where the geometry appears to be flat. That also, though, would lead to an increasing spreading of space. So we would continue to have space would be getting larger and larger. We would be separating from other galaxies. That is the critical density that they've talked about. So what a lot of this comes down to is the density of material and energy. So when we talk about critical density, it doesn't just include how much stuff is out there, but it includes the energy that's contained. Now, when we look out into, let's go back and look at this, what we find right now is that the universe, at least the observable portion of the universe, tells us that the geometry is almost Euclidean. So we don't see evidence for a lot of positive curvature or a lot of negative curvature. And if that really does indicate that the density of the universe is very close to what we call critical density, close to the number right here, well, when we look out into space, we don't see enough stars and galaxies to account for that density. So again, quick recap here. The geometry of the universe that we appear to have suggests that there's much more stuff out there than we are able to observe. What would all of this other stuff consist of? So the most recent estimates have suggested that if this accelerated expansion is taking place, that would need to come from some sort of potential energy, either some different sort of gravitational potential energy, and right now that's being referred to as dark energy. The calculations suggest that could make up as much as 75% of critical density. So we go, oh, maybe we really do have enough stuff in the universe to maintain the geometry that we see, but maybe most of that is actually not atoms and molecules, but some sort of gravitational potential energy or some other sort of potential energy that accounts for the bulk of what the universe is made out of. Now there's a second category. There's what's called dark matter, and that would be material that allows galaxies, for example, to form and galaxy rotation rates to be explained. When we look at galaxies that are rotating, we find that they're rotating much faster than what we would expect given the number of stars that they have. If they really do have the rapid rotation rates that we observe, there doesn't appear to be enough gravity to hold them together. And yet the galaxies do stay together. When we look at galaxies, we don't see that there are a large number of galaxies coming apart. We see that the galaxies appear to be stable. Well, if the galaxies are stable, they would need a significant amount of additional gravitation. And so we've assigned that to something called dark matter. We're not sure what dark matter is. Now, one possibility would be something that's kind of neutrino-like. We've talked about neutrinos. Neutrinos came up in the nuclear physics chapters, and neutrinos have come up again in the elementary particle chapter. It could be that there are other types of particles similar to neutrinos in that they don't interact very strongly. So neutrinos are very difficult to observe because they only interact through the weak force. So if we had other particles like neutrinos, which may carry a lot of mass with them, so weakly interacting massive particles, sometimes called WIMPs, if the universe is flooded with WIMPs, then about 20%, we would need about 20% of the critical density to be made up by this dark matter. So it's starting to look like a possibility. The matter that we're familiar with, what they're calling normal matter, things that are made out of protons and neutrons and electrons and neutrinos, those only appear to make up about 5% of the critical density. Dark matter estimates suggest that dark matter could be about 20% of critical density, and then dark energy calculations suggest about 75%. So independent measurements and calculations of these three components suggest that possibly we have accounted for all of the material that makes up the universe. Possibly. But this is certainly an area of active research and something that continues to be looked at very carefully. So that's sounding like a good place to end, and so we will. So we're going to end right there. There is one additional set of notes that I left in here. It's actually a calculation of a neutron star. So it's calculating if a star collapsed into a neutron star, what would the size be? And you can take a star similar, actually bigger than the sun. I'm not going to go through the details of this, but you could take a star 1.5 times the mass of the sun. So the sun's not large enough to collapse into not heavy enough to collapse into a neutron star, but something 1.5 solar masses would be enough, and if it collapsed into a neutron star, it would only be 11 kilometers across. So that's kind of a remarkable outcome. But again, I'm not going to worry about that. For us, let's just stick with this last slide here, I guess, of what currently we think of as maybe our best estimate as to what the universe is made out of. All right, questions here too. I hope most of this stuff, most of the calculations are going to be similar to things that we've done before. So definitely take a look at the homework problems. Whatever questions you guys have, stop by office hours. This should be really, I hope, a fun and interesting and engaging chapter to work through.